Here I have the dot structure for the ethene or the ethylene molecule, and we can see there's a double bond in this molecule. We can also see that each carbon is bonded to 3 other atoms. So if I look at the carbon on the left, right, it's bonded to 3 other atoms. In the video on sp3 hybridization, we saw that carbon is bonded to 4 other atoms and that carbon has only single bonds around it. So each of the carbons in ethene must have a different type of hybridization. To figure out what type of hybridization these carbons in ethene have, let's look at the orbital notation showing the 4 valence electrons of carbon. So down here I have the excited state, meaning I've already shown one of the electrons being promoted from the 2s orbital up to what used to be an empty p orbital. In the video on sp3 hybridization, once we had the excited state, we took all 4 of these orbitals and we hybridized them to create 4 new hybrid orbitals. And in this example, since carbon is only bonded to 3 other atoms, we only need to create 3 new hybridized orbitals. So to create those 3 new hybrid orbitals, we're going to promote the s orbital up in energy. So here's our s orbital with its 1 valence electron promoted up in energy. And we only need to create 3, so we're only going to demote 2 p orbitals this time. So we go ahead and demote 2 p orbitals. Each p orbital had 1 valence electron in it like that. That leaves 1 of our p orbitals untouched. So we're going to leave 1 p orbital untouched. We're not going to hybridize that p orbital. So now we no longer have an s orbital here. We're going to hybridize it with the other 2 p orbitals to create what we call an sp2 hybrid orbital. This is no longer a p orbital. It's now been hybridized to form an sp2 hybrid orbital. And this last p orbital as well. It's no longer a p orbital. It's now an sp2 hybrid orbital. And we call this sp2 hybridization because our new hybridized orbitals were formed from 1 s orbital and 2 p orbitals. So this is sp2 hybridization. And now we can say that each of the carbons in the ethene molecule are sp2 hybridized, right? So this carbon is sp2 hybridized, and this carbon is sp2 hybridized, like that. Our new sp2 hybrid orbitals, right, were made from 1 s orbital and 2 p orbitals, so we could say that our new hybrid orbitals contain approximately 33% s character and 67% p character. And so when the quantum math is done to predict the shape of our new sp2 hybrid orbital, it's going to have a little bit more s character than what we saw for the sp3 hybridization. So when I show a carbon that's sp2 hybridized, it's going to have, according to the quantum math, a larger frontal lobe and then a smaller back lobe here, like that. Now again, if we compare an sp2 hybrid orbital to an sp3 hybrid orbital. An sp2 hybrid orbital has more s character, and we know that an s orbital is a little bit smaller than a p orbital. So the fact that an sp2 hybridized orbital has more s character than an sp3 hybridized orbital means that these are going to be a little bit smaller, right? My orbitals are going to be a little bit smaller in an sp2 hybrid orbital than an sp3. And this is going to affect the length of a bond when we're talking about carbons that are bonded together that are sp2 hybridized. Let's go ahead and try to draw the ethene molecule showing these sp2 hybrid orbitals, right? So if I go back up here and look at the dot structure for ethene, each carbon in ethene is sp2 hybridized. So each carbon in ethene is going to have 3 sp2 hybridized orbitals. Each orbital is going to contain 1 valence electron. So let's see if we can draw that. We're going to try to show the ethene molecule, and I'll start with the carbon on the left here, and it's sp2 hybridized, so it has 3 sp2 hybrid orbitals. Once again, I'm going to ignore this back lobe here because it's too confusing, so I'm just going to put the front lobe, and I'm saying that represents an sp2 hybrid orbital. Alright, I need 2 more, so this carbon has a total of 3 sp2 hybrid orbitals. Each hybrid orbital has 1 valence electron, so I'm going to go ahead and put in the 1 valence electron, like that. Alright, there are 2 carbons in ethene, right? Each carbon is sp2 hybridized. So this other carbon also has 3 sp2 hybrid orbitals, and each of those orbitals also has 1 valence electron. So I'll go ahead and put in my valence electrons. All right, there are 4 hydrogens in the ethene molecule, 2 hydrogens on each carbon. The hydrogen has 1 valence electron in an unhybridized s orbital. An unhybridized s orbital is shaped like a sphere, right? So this is the s orbital of a hydrogen atom, and there's 1 valence electron. So I'll go ahead and put in the 1 valence electron in there like that. So I can go ahead and put in the second hydrogen with its 1 valence electron, and then two more for the carbon on the right. Okay, let's go back up to my orbital notation here. So we can see that each sp2 hybridized carbon has an untouched, unhybridized p orbital with 1 valence electron. P orbitals are shaped like dumbbells. So let's go ahead and draw in the unhybridized p orbital on an sp2 hybridized carbon. So there's my p orbital, and there's 1 valence electron in that p orbital. All right, this carbon on the right, since it's also sp2 hybridized, it also has an unhybridized p orbital shaped like a dumbbell with 1 valence electron in it like that. Now that we have the picture of the ethene molecule, let's analyze the interaction of these orbitals. So if I look at these two sp2 hybrid orbitals between my 2 carbons, right, they're overlapping in a head-on fashion, right? And we said that head-on overlap is a sigma bond, right? So there's a sigma bond between my 2 carbon atoms like that. There's a head-on overlap between the sp2 hybrid orbital of this carbon on the left and this s orbital of the hydrogen. So that's a sigma bond. This must be a sigma bond, right? This must be a sigma bond, and then this one as well. So there are a total of 5 sigma bonds in the ethene molecule. Let's look at these p orbitals. There's no way that these p orbitals could possibly interact in a head-on fashion. The only thing they could possibly do is if they were big enough, you could think about them overlapping in a side-by-side fashion, right? So a side-by-side overlap of p orbitals is called a pi bond, right? So this is a pi bond here, a pi bond, and there's only 1 of them in this molecule. So in this molecule, there are 5 sigma bonds and 1 pi bond for the ethene molecule. Let's look at that sigma bond that's in between my 2 carbon atoms, right? So I'm looking at this sigma bond right here in between my 2 carbon atoms. Remember that we said sp2 hybridized orbitals are smaller than sp3 hybrid orbitals, and that means that these 2 carbon atoms are closer together in space, which means that the bond length is shorter, right? So since these carbons are sp2 hybridized, it's going to be shorter. And since we have 1 sigma bond between my 2 carbons and 1 pi bond, this is a double bond. And so this is one way to explain why a double bond is shorter than a single bond. It has to do with the fact that sp2 hybridized orbitals are smaller than sp3 hybridized orbitals. Let's draw one more picture where we can show the p orbitals a little bit more clearly. So I'm going to go ahead and sketch in the ethene molecule one more time, and I'm first going to show the single bonds, right? So the 5 single bonds, the sigma bonds. So this is the skeleton of the molecule. And I think this is a good time to point out that it's these hybridized orbitals that are going to help determine the geometry of the molecule. So the ethene molecule turns out to be planar overall. So everything is planar. So you could think about all these atoms being on the same plane, like a flat sheet of paper, like that. And when we go ahead and draw in our pi bonds, pi bond, there's only 1 of them here, right? This carbon has a p orbital. I'll draw it a little bit bigger, right? And this carbon also has a p orbital. If I draw it big enough, I can show the fact that they can overlap side by side like that, right? So maybe I should have chosen a different color here, but you can see that there's some side by side overlap above and below the single bond between the 2 carbon atoms. And so this pi bond is going to prevent free rotation, right? If there were only a single bond between those 2 carbon atoms, we could have free rotation about that bond. But the presence of the pi bond prevents free rotation. So when there's a double bond, there's no rotation between the 2 carbon atoms. One thing that confuses students sometimes is they see the fact that there's 2 areas of overlap, and so they think that must mean there are 2 pi bonds. But that's not the case. That's just the quantum probability of finding your electrons. There's really only 1 pi bond here, right? So there's 1 pi bond. which prevents free rotation. But when you think about the hybridized orbitals, right, so that creates your single bonds, that will determine the bond angle, right? So since everything is flat, and we think about VSEPR theory, right, these electrons in the hybridized orbitals are going to repel each other and get as far away from each other as they possibly can. And so since this is all on a plane, right, we would have 360 and divide that by 3 to find the bond angle, right? So it's approximately 120 degrees. And so this picture helps us to understand the bond angle, the geometry of the molecule, and also the fact that there is no free rotation, right? So let's go ahead and let's just draw the dot structure one more time for ethene and analyze it using all that we've figured out here. All right, so if you look at a dot structure and you're trying to figure out how many sigma bonds and how many pi bonds, you just go ahead and count up your single bonds, and those are your sigma bonds, right? So if I go ahead and highlight those, so this is a single bond, so that's a sigma bond, so here, right, here, and between those two carbons, I know one of those bonds is a sigma bond and one of those bonds is a pi bond. It doesn't matter which one you say it is on the dot structure, so I'm just going to say it's that one, right? So I can see my 5 sigma bonds like that. And then for my pi bond, I just said that this top one was the pi bond. It didn't really matter which one you said, so that's the pi bond. So that's how to look at a dot structure and analyze sigma and pi bonds.